Hello everyone, welcome back to the channel. This is another video on Norton's theorem. In previous video, I had shown you that how to obtain Norton's equivalent of a complicated circuit. We had even solved two numerical problems. In this video, I will take three more problems which will be solved by Norton's theorem only. The circuits will be different in comparison to the previous ones. Let's start with the first problem. Problem is using Norton's theorem, find the current through 10 ohm resistor. This is the first problem in which we have three different voltage sources, multiple resistances are there. This one is 10 ohm, basically the load resistance, 20 ohm, again 20 ohm, 20, 30, and last voltage source is supplying 100 volts. So this is a circuit. We need to find out the current through 10 ohm resistance. So basically these two are the load terminals, marking them as A and B. Now in order to obtain the Norton equivalent, we have to replace the whole circuit except this 10 ohm resistance by a single current source in parallel with single resistance. The value of that current is equal to the short circuit current through load terminals. So our first step is obtaining ISC. Now for obtaining ISC, what we need to do, we need to replace the load resistance by short circuit. A, B, this 10 ohm resistance, it will be replaced by short circuit. The rest of the circuit will remain as it is. All the resistances and voltage sources except the load resistance will remain at their place with same values. We need to find out the current over here, that is ISC. Now in this problem, in order to find ISC, we can't apply nodal analysis since we don't know that what is the resistance in this branch. It's unknown. Not unknown, it's basically zero because we have only a voltage source in series with the short circuit. Short circuit means zero resistance. So the resistance of this branch is zero. So we can't write the current by using nodal analysis. So what we need to do in this case, we need to apply mesh analysis in order to find out the current ISC. So we have three meshes. Let's assign all currents clockwise: I1, I2, I3. Starting from first mesh, mesh 1, I will start from 50 volt source, minus 50, then drop across 20 ohm. Polarity is marked as per the flow of I1. So plus 20 into resultant current in direction of I1 is I1 minus I2, plus 40 equal to 0. So this will give us equation 20I1 minus 20I2 equal to 10, or 2I1 minus 2I2 equal to 1. This is the first equation corresponding to first mesh. Then we have second mesh. Now let's mark the voltage drop across each resistance with respect to current I2. Since I2 is flowing from this terminal to this one is positive, this one is negative, upper terminal positive, lower negative, and for this 20 ohm, lower will be positive, upper will be negative. So mesh 2 equation, starting from this 20 ohm resistance, 20 into I2, then moving on to next 20, that is this one, plus 20 into I2 minus I3, that is the resultant current through this 20 ohm resistance in direction of I2, minus 40, and then the last resistance 20 ohm, which is common to second and first mesh, 20 into I2 minus I1 equal to 0. Now when we solve this equation, we have minus 20I1 plus 60I2 minus 20I3 equal to 40, or minus I1 plus 3I2 minus I3 equal to 2. This is our second equation. And then we need to apply KVL to mesh 3. Now for mesh 3, we have to assign the voltage drop as per the direction of I3, plus minus, then we have voltage source. This terminal of 20 ohm resistance is positive, this is going to be negative. Starting with 30 ohm plus 30 into I3, then for voltage source positive sign is coming first, so plus 100, plus drop across this 20 ohm, 20 into I3 minus I2 equal to 0. This is the third equation. So this equation will give us minus 20I2 plus 50I3 equal to minus 100, or minus 2I2 plus 5I3 equal to minus 10. So the third equation. Now when we solve these three equations, first, second and third, simultaneously, we will get the value of I1, I2 and I3. I1 is 0.8125 ampere. Basically, we are interested in the answer of I1 only, because I1 and ISC both are same. But still I am giving the answers of I2 and I3. I2 is 0.3125 ampere and I3 is minus 1.875 ampere. But from here, I1 is flowing in this direction, ISC is also flowing in this direction. So I1 and ISC both are same. Short circuit current is equal to I1 is equal to 0.8125. So we got the one answer, that is the short circuit current. Second is we need to calculate Rn. Now for calculating Rn, all the voltage sources, they will be replaced by short circuit. 50 volt source replaced by short circuit, 40 volt replaced by short circuit, 100 volt replaced by short circuit, and we will open the terminals A and B and calculate the equivalent resistance seen from these terminals. Let's redraw the circuit again. A, B. Short circuit, then here we have 20 ohm resistance, then 20 ohm, again 20 ohm, 30 ohm, 100 volt source replaced by short circuit. And we need to calculate Rn over here. So when we need to calculate the resistance over here, so we have to start from the opposite side. Opposite side means from here, from these terminals. Now when we start from here, firstly we have 30 and 20, they are in parallel. So we can replace it by 30 in parallel with 20. Here we have 20 ohm, this one is 20 ohm. Now it becomes clear that this 20 ohm is in series with this 30 and 20 parallel combination, and the whole resultant is in parallel with this 20 ohm. Now how they are in parallel? Because if we connect any source over here, that current will get divided, any current flowing from here, that will get divided into two parts. Like one part will flow through this 20 ohm and second part will flow through the series combination of this 30 and 20 parallel and this 20. So Rn is actually 20 plus parallel combination of 30 and 20, and this whole again in parallel with 20. When we solve this, then Rn is 12.31. Now you can solve this by your own and check your answer. Once we have the value of In, that is short circuit current, and Norton resistance, then we can draw the Norton's equivalent. Rn is 12.31. We have calculated the short circuit current, this one, which is actually Norton current. So it's 0.8125 ampere. And in parallel, we have to connect the load resistance, and that resistance value was 10 ohm, and we had to find out the current through this 10 ohm. This was the question. Question was current through 10 ohm resistance. Now we can apply current division rule. So I 10 ohm is equal to source current, that is 0.8125, to opposite branch resistance 12.31, opposite branch resistance plus load resistance. So this answer is 0.448 ampere. This is the answer for current through 10 ohm resistance. Now let's move forward to another problem which will look similar to this. Question is, obtain Norton's equivalent of the circuit shown below across terminals of RL. So RL is given in the network. So this problem actually is quite similar to the previous one. The only difference is here we have to just find out the Norton's equivalent across these terminals. These terminals are shifted from here to this side. The rest of the circuit is almost same. So the procedure for calculating ISC, that is exactly same as the previous one. For calculation of RL, again we will have similar type of equivalent circuit. Now let's calculate ISC. Now for calculating ISC, we have to replace this load resistance by short circuit. The rest of the circuit will remain as it is, like in the previous case. A and B replaced by short circuit. Here we have minus plus 10 volts. Again, since we have only a voltage source between these two nodes, so we can't apply nodal analysis over here to find out the current through terminals A and B, that is the short circuit current. So we have to go with the mesh analysis only. I'm assigning the current to this mesh as I1, I2 and I3. So ISC is actually equal to I3. We need to find out the answer of ISC in this case. Let's start with first mesh, plus minus plus minus. Now these are the voltage drop polarities as per the flow of I1. So mesh 1 equation is minus 120 plus 30 I1 plus 60 I1 minus I2 equal to 0. 90 I1 minus 60 I2 equal to 120. 3 I1 minus 2 I2 equal to 4. First equation. Then mesh 2, voltage drop polarity across 10 ohm, 30 and 60. Start with 40 volt source minus 40 plus 10 into I2 is the drop across 10 ohm resistance. 30 into I2 minus I3 is the voltage drop across 30 ohm plus 60 into I2 minus I1 is the voltage drop across 60 ohm resistance. So we get minus 60 I1 plus 100 I2 minus 30 I3 equal to 40, or minus 6 I1 plus 10 I2 minus 30 I3 equal to 4. This is our second equation. Third equation from mesh 3. In mesh 3, this is the voltage drop polarity as per the direction of I3. Minus 10 plus 30 into I3 minus I2, that is the resultant current in direction of I3. Minus 10 plus 30 into I3 minus I2 equal to 0. So this will give us equation minus 3I2 plus 3I3 equal to 1. This is our third equation. So simultaneous solution of 1, 2 and 3 will give us the value of 3 mesh currents. I1 comes out to be 4.22 ampere. I2 is 4.33 ampere and I3 is 4.67 ampere. So this is the value of short circuit current or Norton current. The next step here is calculation of Norton resistance. For Norton resistance, 120 volt, 40 volts, 10 volt, they will be replaced by short circuit. Load resistance replaced by open circuit, because we have to find out the equivalent resistance seen from these two terminals. 30 ohm resistance, 120 replaced by short circuit. Then we have 60 ohm is 40 volt replaced by short circuit. 10 ohm, 30 ohm, this is Rn. So we have to start from the opposite sign. 30 and 60, they are in parallel. Their parallel combination is in series with 10, and that whole resultant is in parallel with 30. So this one is exactly similar to the previous one. Only difference is earlier these two were the terminals, now these two are the low terminals. 30 in parallel with 60 This combination is in series with 10 ohm. Then the sole is in parallel with 30. And when we solve it, we get the value of Rn as 15 ohm. The Norton's equivalent is 4.67 ampere in parallel with 15 ohm. This RL. So this is the Norton's equivalent which was asked in the problem. Now the last problem which we consider over here is statement is determine the Norton's equivalent for the given circuit across terminals A and B. So let's draw the circuit. This one is A and this terminal is B. So basically these are the load terminals. We have to obtain the value of short circuit current through these load terminals, and also we need to find out the equivalent resistance seen from the load terminals. First part is the calculation of ISC. For calculating ISC, we have to short circuit the load terminals. Let's draw all the resistances. Mark their value: 3 ohm, 4 ohm, 2 ohm, 8 ohm, 25 ampere source, and this one is 5 ohm. This A and this one is B. Now short circuit these terminals. Now when we short circuit these two terminals, whatever the current is coming from this 4 ampere, whole current will flow through the short circuit only. The current through 8 ohm will be 0. Or otherwise what we can say, this 8 ohm is in parallel with short circuit. Short circuit means resistance is 0. When we solve this parallel combination, the equivalent resistance is actually 0. That's why the 8 ohm resistance is actually no longer existing in the circuit. It is having no impact on the current flowing through the circuit, or the current through the 8 ohm resistance is 0. So we can just remove that resistance. Now we need to find out the current through this. So that current is ISC, that is short circuit current. Now in this problem, it's very easy to find out short circuit current because we have a current source connected in series with 5 ohm. So current over here is 25, which will get divided into two parts across this 2 ohm and a series combination of 3 and 4. So we can apply current division rule. ISC will be equal to source current. Source current is 25 to opposite branch resistance. This 25 ampere is getting divided in two parts. Opposite branch resistance is 2, and in denominator it's 2 plus series combination of 3 and 4 plus 3 plus 4, that is 7. So it's 50 by 9, which is 5.556 amperes. ISC is 5.556 amperes. Next step is we need to calculate Norton resistance. Now for calculating Norton resistance, the current source is replaced by open circuit. The rest of the resistances will remain as it is. 5 ohm, 2 ohm, 3 ohm, 4 ohm, 8 ohm, and these are terminals A and B. We have to find out the equivalent resistance seen from terminals A and B. Now this 5 ohm resistance, it's not having any impact on the equivalent resistance of the circuit since its one side is open. So 2, 3 and 4, they are in series and their series combination is in parallel with 8. For that you can assume that if any current is flowing from this terminal A, how this will flow. This will get divided into two parts. Then from 4 to 3, 3 to 2, because on this side it's open, no current will flow through 5 ohm. It means 3, 2 and 4, they are in series and that resultant is in parallel with 8. So Rn is 2 plus 3 plus 4 and that is in parallel with 8. So 9 in parallel with 8, which is actually 4.235 ohm. So then we have to draw Norton's equivalent. Now Norton's equivalent is a current source connected in parallel with the resistance, and here we will have terminals A and B. Current source value was 5.556 ampere. Rn is 4.235 ohm. So I'm ending over here. I had taken 3 problems in this case, which were a bit complex in comparison to the previous video, but still we haven't covered the problems where we have dependent source in the circuit. All these problems were the related to circuits where we are having only independent sources. In next video, I will show you that how to obtain Thevenin's equivalent or Norton's equivalent when we have a dependent source present in the circuit. Thank you for watching the video.